tangent line approximation and local linearity. So one of the things that's really powerful that we can do with derivatives is use the information we have about the function and its rate of change at a point to make a good prediction about what might happen at nearby points. The way we do this is something called tangent line approximation using local linearity. These refer to the same process. So the idea is that we can find an approximation of the value of a function at a point if we have information about a nearby point and information about the derivative of that nearby point. And therefore, we can use the formula f of x is approximately f of a plus f prime of a times delta x. So let's talk about what these pieces mean. So f of x is the new point that we're interested in. So this might be f of 2, and we have information about f of 1, but f of x is where we're interested in finding out what we think is happening there. F of a is the place where we have information. We know the value at a. F prime of a is the derivative or the rate of change at a. So we need both these pieces, the functional value and the derivative value. Delta x is how far away from a we are trying to predict. So if we know information about f of 1 and f prime of 1, and we're using that to make a prediction about the value of f of 2, then delta x would be 1 because we'd be moving 1 unit away from 1 to 2. However, if we are going to use our information to make a prediction about something that happened before the information we have, so let's say that f of a is at 1 and f prime of a, we're looking at 1, and we want to use that to try to predict what was happening at 0, then delta x would be negative 1 because we would be moving backwards. So what's happening is that we have some function and we have information about what's happening at one point. So if we know the derivative and the functional value, what we're going to do is we're going to use that to predict what's happening at some other point by just using the slope of a line. So we're just assuming that this rate of change is going to be constant until that point to get a good approximation of where it would be. Now, this is valuable if we don't have the whole function. If we have the function, like we do in this graph, we could actually get the value at b. But the idea is that we wouldn't know the whole function. We would just know information about what's happening at one point. And we want to use that to talk about what's happening at a nearby point. Now, how good this approximation is wholly depends on how close you are to the point where you have information. If you have information about what's happening at 1 and you want to use that to predict what's happening at 10,000, that's not going to be a very good approximation. However, if you have information about what's happening at 1 and you want to use that to predict what's happening at 2, that's going to be fairly good. So keep in mind, closeness dictates how good your approximation is. So let's look at a couple of examples of how we use this particular function to approximate what's happening. Suppose that a particular function has g of 5 equals 10 and g prime of 5 equals 3. Use this information to approximate g of 7 and g of 1. So again, the two things we need to be able to do local linear approximation is we need information at a point and information about the derivative at the same point. So here the information we have happens at the point x equals 5. So we're going to use this to try to make an educated approximation for g of 7 and g of 1. So these are two different problems. So let's start with g of 7. So our formula says that f of x is going to be approximately f of a plus f prime of a times delta x. Well, here, this is my f of a, and this is my f prime of a if I'm matching it up to the formula. Of course, I'm using g here, but what we call the function doesn't matter. So that means g of 7 will equal g of 5 plus g prime of 5 times delta x. Now, delta x is how far away I'm moving from the information I have to the information I want. So since I'm going from 5 to 7, I'm moving forward 2 units. So my delta x is going to be 2. So now that I have things plugged into the formula, I want to plug in my values. So the value at 5 is 10, and the rate at which my function is changing at that point is 3, and I'm moving 2 units away. Now here, I want to remind you that we need to multiply the 3 and the 2 before we add that to the 10. Multiplication needs to happen before the addition. So we have 3 times 2, which is 6, plus 10, and that's going to give us an approximation of 16. So again, the idea is that if the functional value is 10 at 5, and we're changing by 3 units in the dependent direction for every 1 unit in the independent direction, if we're moving 2 units away, likely our function is going to go up to 16. Again, this is just an approximation, but given that we don't know anything else about the function, this is the best we can do with the information that we have. Similarly, if we wanted to approximate g of 1, we still have our information at the point 5, but now our delta x is going to change. So before, we were going from 5 to 7, moving in the forward direction, but now we're going from 5 back to 1. So if we go in the leftward direction or backwards in time, if you have a time problem, that means your delta x is negative. So here, when we move left 4 spaces, we're going to write that as negative 4. So again, we plug in our values. And again, we're going to do the multiplication part first. 3 times 4 is negative 12. And negative 12 plus 10 is going to give me negative 2. So my approximation for the value of this function at 1 is negative 2. So again, a couple things we have to be careful about. With your delta x, if you're moving backwards from the point you have, your delta x needs to be negative. The other thing we said was important is that you multiply before you add when you're plugging things into your formula. And then finally, all of these are approximations. None of these are exact. So we're not going to use equal signs with our final answer. We're going to use approximations. And again, how good your approximation is depends on how close you were to the information you had. So here, that means that g of 7 was a better approximation than g of 1 because g of 7 was within 2 units, whereas g of 1 was 4 units away. And the further away you get, the worse your approximation is. Let's take a look at another. Suppose the population of a town was recorded starting in 2000. In 2006, the population of a town was 125,000, and the town's population was increasing at a rate of 3,200 people per year. Use this information to approximate the size of the population in 2013. So here, we want to start by writing down the information we have. We know what's happening in 2006. We know the size of the population, and we know the rate, which is the derivative in 2006. There's 2 different ways we can write this. We can assume that in 2000, that t would equal 0, in which case we could write p of 6, the population 6 years later, so 2006, equals 125,000. And the rate that the population was increasing, so that's the derivative in 2006, was 3,200 people. Exactly the same, we could have done p of 2006. We could put the year right in because it doesn't tell us how we have to use our t. Is 125,000. And p prime of 2006 is going to be 3,200. These are the same exact thing. I'm going to stick with the stuff on the left because I like to set time equal to 0 when I start measuring, but you could have done this either way. Now, we want to use this information to approximate the population in 2013. So since I started measuring in 2000, I'm interested in p of 13. So that's going to equal the point I have plus the derivative at that point times delta x. So to go from 2006 to 2013, or time equals 6, to time equals 13. That's 7 years forward, which means I'm going to be multiplying my derivative by 7. My delta x here is going to be 7. So again, I'm going to carefully plug in these values. And again, I'm going to multiply 3,200 times 7 first, and then add 125,000. And I'm going to get that my population in 2013 is approximated as 147,400. Now, most likely this is people, because we're talking about a town, but it doesn't specifically say people, so we don't really need to add units. We can just say we approximate the population to be 147,400. So again, with this problem, we need to take the information we have about the numbers and turn them into functional notation so we could then apply our formula to what we had. Suppose the table below gives the total sales in millions of CDs for a music store as a function of time in years. So what this means is that in 2008, 6.25 million CDs were sold, whereas in 2012, only 4.25 million CDs were sold. We want to use the table above to estimate the sales in 2013 using local linear approximation. So remember that in order to use local linear approximation, we want to use the functional value and the derivative at that point. So we have functional values here. For example, f of 2008 is 6.25, f of 2009 is 6.06, so on and so forth. Also, let's remember that our approximation is better the closer we get. So instead of using 2008 to approximate what's happening in 2013, we would have a better estimate if we used 2012. So let's start there. We know that f of 2012 equals 4.25. That's the number on this table that's closest to 2013. So we always want to get as close as possible to make our approximation as good as we can. Now, in order to be able to use local linear approximation, we also need the derivative at 2012. Notice that we didn't have the derivative in the setup of the problem here. However, in past sections, we learned how to approximate the derivative using average rates of change. So what I can do is I can do the average rate of change with the closest point to 2012 to give me an approximation for the derivative. So doing the average rate of change, I'll do the change in y over the change in x. So 4.25 minus 4.7 divided by 2012 minus 2011. So when I crunch that number in my calculator, I'm going to get negative 0.45. So now I have an approximation for the derivative. So I can now use local linear approximation to get an estimate for the value in 2013. So 2013 is going to be the value at 2012 plus the derivative at 2012 times delta x. So my delta x here is going to be 1 because I'm trying to go from 2012 to 2013. So that's forward 1 year. So my delta x here is going to be 1. So now I need to plug in the numbers to see how this number shakes out. So f of 2012 is 4.25, and this again is in millions of CDs, plus the derivative is negative 0.045, and this is in millions of CDs per year. And this is 1 year, right? So the years units are going to cancel. And I'm going to multiply the 1 times the negative 0.45. And anything times 1 is itself. So when I crunch this number, I get 4.25 minus 0.45, and I get 3.8 million CDs as my approximation. Now, as we said before, the further away you move from a point, the worse your approximation. However, I also want to add in that if we have to approximate the derivative to even use this function, that also weakens the approximation because we don't know the exact rate of change in 2012. That was an approximation used to make another approximation, and therefore it's not as good as if we had actually had the derivative at 2012 from some other means that was more accurate. However, given the information we have, this is the best we can do to predict what the sales would be in 2013, which would be 3.8 million CDs is the prediction based on the table and the data we have.